Today we're going to finish up section 3.2. We had started last time talking about addition and subtraction of whole numbers, and we had gotten to the part where we were going to look at some properties. All right, there are 4 properties of whole numbers for addition. The first property is called the closure property. This one is the one that trips people up the most. The property in and of itself is very straightforward. It says that if I have 2 whole numbers and I add them together, I get another whole number. Okay? This is specifically true for whole numbers. It's not true for all numbers. For example, if I were to take a decimal, like a true 0.4 decimal or something like that, right? And I added it to another decimal, I would not necessarily end up with a decimal, right, that's requiring the decimal point kind of number. Right? That's not true in that sense. If you were to add fractions, you'd have the same sort of thing. Right? 2 fractions don't necessarily equal another traditional, like we think of, fraction. Or maybe you added 2 improper fraction or proper fractions. You could actually end up getting an improper fraction, right? So this is very special to the fact that we're dealing with whole numbers. But there are other things that do have this property. For example, let's say you added together an even number and an even number. Do you always get an even number? Yes, you do. So even numbers have this property as well. So some groups of numbers have closure and some groups of numbers don't. One way to think about it is think about having all the whole numbers floating around inside of our room. They're just all floating in the air, right? And if you were to take any 2 of them and you were to add them together, you would get another whole number that's still floating around inside the air in the room because it's a whole number. And the door's closed. But if I were to have to go and get a number that's not floating around in my room, I would have to open the door. It would no longer be a closed operation. Okay? So that's what closure is. For example, if you took odd numbers, are odd numbers closed under addition? No, they're not. An odd number plus an odd number actually never equals an odd number, does it? It doesn't. So that is not a set that's closed with respect to addition. The second one is the commutative property. The commutative property says that the order of addition doesn't matter. Whole numbers in addition, right? So if I take A plus B, it's equal to the same thing as taking B plus A. And kids work with this all the time without sort of thinking about it, right? It's going on in the background of the problem. So when kids are first learning their addition, like addition tables, right? Flashcards and things like that, all that good stuff. And you go, we do the ones, and we learned what 1 and 1 is and 1 plus 0 is, and then we add on the 2s, and we get 2 plus 1 and 2 plus 0, and we also still have the 1 plus 1, and we add these things on, right? Eventually, we're not adding on a whole bunch at a time because we're just building up to that, right? Eventually, when I do the 8s and I do the plus 8s, I don't really need to add 8 plus 1. I already know what it is because I learned 1 plus 8 before. You with me? So the commutative property is one that kids use, again, behind the scenes quite a bit. Another property that's used behind the scenes quite a bit is called the associative property. The associative property says that I can regroup numbers. So A plus B, added together first, and then adding C on, is the same thing as adding B plus C and then adding A on. Right? We work inside parentheses before we move to the outside of parentheses. I talk about or think about the associativity property because the associative property and the commutative property, people will get confused with one another. Commutative has to do with the fact that you're switching the orders, right? If I go from here to my house or I drive from my house to here, it's the same distance, right? The order didn't matter. It's the same thing. But if I do the associative property, it's like who I'm associating with. So you see the parentheses present that's showing the association that's being made. The last property is called the identity property. And the identity property says there's a unique whole number 0. It's called the additive identity. That's what this number is called. So if I ask you what is the additive identity, it's 0. Okay, that is the additive identity. And the reason that it's the additive identity is because when I add it to anything, it doesn't change the thing I add it to. 0 plus A or A plus 0 is still A. And you use this property a lot. You'll use it when you are working with equations, right? If I add something to both sides of the equation, it's the identity doesn't change the evaluation of the equation. Sometimes we change things with a multiplicative identity, which we'll get to in a couple of sections as well. So there's more than one type of identity property. This is the additive identity property. And so what we're going to do is we're going to do 4 examples where I would like for you to write down what property you believe it is, and then grab somebody nearby and see if you got the same properties. Check in with a neighbor when you get finished, well, and you and your neighbor both get finished. And see if you have the right idea together. What do you think the first property is? What is A? It is commutative. Commutative is one of those words that's kind of a pet peeve for me when people spell it wrong, because they usually change it in such a way it turns into a different word, like communicative or something like that. So check out how you're spelling it. Make sure it actually says commutative. How about the second one? What property is that? It's the identity. Yes, it is. Don't let the fact that there's parentheses around part of it throw you. And specifically, what kind of identity? The additive identity. And while it doesn't really make sense in terms of this lesson, or it's not that it doesn't make sense, it's not necessary, it will be later when we have 2 identities. So please make sure you write down additive identity to distinguish it from the other one we'll learn later. How about C? Okay, so commutative for sure. So what changed for commutative to be present? What did you notice? All right, the order of the 8 and the 6 flipped, okay? But it is not associative, okay? Associative would mean that the parentheses themselves are around different numbers than they were originally around, and this one isn't. So remember, just because there's parentheses present doesn't necessarily mean there's associative. How about D? Okay, so that one would be, what did you have? Associative, I agree. Please don't abbreviate that one, that's a bad idea. All right, so again, the parentheses here are around the 5 and the 3. The parentheses here are around the 3 and the 2, but the 5, the 3, the 2 are in the same order on both sides. So there's no associative, there's no commutative going on. If the order of the numbers had also changed, we would have had 2 properties there, right? Yeah. Yes, Emily?
If like there was parentheses 5 plus 3 and then plus 2, like on the left side, that's the same. And then you had in parentheses 3 plus 2 and then plus 5.
Yes.
Then it would also be.
Well, then it would be commutative, but it would not be associative, because
the 3 and the 2 are still paired together.
if the pairing is still the same, then it's not commutative, or it's not associative.
Right. So on the first, the left hand side, it's the 5 and the 3. But then on the right hand side, if it's just put the 5
Oh, you said, like if you did this.
Yeah, 3 plus 2.
Whoops, that was supposed to be a 2. Like this, then yes, it would be both.
Okay.
You're right. Yeah, because we would have done a commutative property with the parenthesis parts too. Cool. All right, we're going to look at some basic addition and subtraction strategies. Some of these maybe you have heard before, maybe you've used them before. Some of them maybe you haven't, but they're good ones to be aware of because it's hard to know exactly what your curriculum is going to look like when you get in your classroom. So seeing it now for the first time would be better than seeing it in 3 years for the first time, right? Yeah, for sure. So the first one is one that I think is pretty common. It's called the counting on addition strategy. And so if you have two numbers, you start with the one value and you count up the additional amount to the other value. So you'll see people do this one a lot. So if you had something like 5 plus 3, you'd start with 5 and you'd go 6, 7, 8, right? You'd count up 3 more from the 5, and then your answer would be the answer you end at. So that's counting on strategy. Doubles has been really popular at different points in the curriculum. I know that one of my children studied doubles. The other one did not as they were going through the elementary school ages. So basically it's the idea that we're going to learn all the doubles. We're going to learn 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4, 5 plus 5, and so on. And that's where we start the addition part. And then when we look at finding like 3 plus 4, we think about it as, well, I already know 3 plus 3, and so this is just one more than that. Okay? So if I know 3 plus 3 and I know that that's 6, then 3 plus 4 must be 7. It's one more. That's the doubles strategy. Got to be honest, I'm not a fan of this strategy. I don't see it as being that profitable for my child when they learned it that way. I mean, we went through the motions, but to me, I don't like this one very much. But it might be in your curriculum and you might be required to teach it, so be aware of that. Making 10 is a pretty cool strategy, and it gives very good justification for why the associative property is valuable. So the making 10 idea is the idea of breaking pieces apart and grouping them together in such a way that you make 10. For example, 8 plus 6, what we could do is we could break the 6 apart into 2 and 4, right? So this 6 is 2 and 4 right here. And the reason that might be helpful to do is because 8 plus 2 is 10. And then 10 plus my 4 would be 14. Okay? You might look at that and go, well, why wouldn't you just learn 8 plus 6? Well, there's some reasons why. And there's some reasons why the double strategy also exists. Is there are children with special needs that don't memorize very well. And maybe even some of you have been that way when you're at that age. Memorization is a real struggle. There are cognitive issues, there are delays in such a way that having strategies to fall back on when you can't just memorize it and remember it are very useful. Something else that's really nice with this is when you're used to breaking them apart this way, it's also easier when you have a list of numbers to shuffle things around into tens. We'll see that happen. I can't remember if it's in this lesson or another one, where you're shuffling the numbers around and adding together the convenient values to add together first, instead of just breaking numbers apart to add them together that way. Okay, so this is called making 10. These are a couple of subtraction strategies. One is counting back, and then one is counting on. So counting back works like this. You start with the higher value, and you count backwards to the lower value. So let's say that you had 15 minus 6. Okay, so there's 15, and we're going to count until we get to 6. So we're going to have 14, 13, 12, 11, 10, 9, 8, 7, 6. I did it on my hands so that you could see it. And when I'm done, the number of fingers that I have up was the answer to my question, which would have been 9. Okay, so that's counting back. Counting on means starting with the lower value and counting up to the higher value. So again, it's a subtraction strategy. 15 minus 6. So you start with 6, and instead of going from 15 back to 6, you go from 6 up to 15. And you're still counting again. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and the answer is 9, because I've passed through 9 numbers to get that to happen. Whether you're doing it on your hands, whether you're doing it with concrete manipulatives written down, whether you're doing it with a number line where you're counting spaces, you can do any of those strategies on top of these basic methods as well. Any questions over those? And this is not like a comprehensive list. There's other things too. These are just several of them that your book mentions. to be aware of, okay? All right, definition of subtraction. For any whole numbers A and B, where A is bigger than B, A minus B is the unique whole number C, such that B plus C equals A. And if I put some numbers in, you're going to be like, oh yeah, for sure. So let's do one. Let's say we do 6 minus 2. Okay, 6 minus 2 equals something. I know you know what it is, but just play dumb for a minute. Okay, just pretend like you don't. The idea is that it's going to equal whatever I'd have to add to 2 to get to 6. And what would that number be? It's 4, right? So that's how subtraction is defined. And in fact, that is often how teachers will teach subtraction to start with. If you know your addition facts, you know your subtraction facts. It's just missing pieces in the process of adding them up. You'll notice there was a restriction, I guess, over here that A has to be greater than or equal to B. And the reason, of course, is that if you had, say, 4 and it's less than 6, like that, then 4 minus 6, while it can be subtracted, you wouldn't end up with a whole number doing so. That's why that restriction's there, just so that you're aware of it. Nothing super sketchy or strange about it, but just that's why it's there. All right, there are 1, 2, I think it's 4. Yep, there are 4 models for subtraction. So let me talk to you about all 4 of the models. We talked about 2 models for addition last time. And then we're going to do a little group activity. It's not a lengthy one, but a group activity about models for subtraction. The first model is the model that people often think about as a description of what subtraction is. In fact, if you ask a child what is subtraction, they will often use the phrase takeaway. Okay, so that's a very ingrained upon us idea of what subtraction means. Takeaway. So Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? So you have something, and you're going to be taking part of it away. That's the takeaway model. It doesn't even have to be whole number objects, but when we get into partial objects like I need to, I have 24 cups of flour, and if I take away 4 cups of flour, how many cups do I have left? That actually crosses the line at least a little bit into what we call the measurement model, which we'll get in a minute, because it's partial amounts of things, right? I can break a cup down into a half a cup, right? Rocks don't work quite like that, right? It's a rock or it's not a rock. It's not a half a rock, okay? So when we're thinking about this model, we have something and we're removing part of it, giving part of it away, having part of it taken away from us, something like that. And we can actually draw a concrete image with this. You can do this with concrete objects, of course, as well. So go ahead and draw with me. I could at least make my rocks brown, I guess. Draw with me 24 rocks. Did I say 24? Yeah. So in terms of a visual demonstration, if I started out with 24 rocks and Eli comes and takes some of them away, right? How many rocks are left? Had 24? 19, right. So there's 19 rocks. And remember to put the word rocks, right? 19 rocks remain. Now, the model is the language of the fact that there was something removed. This is the solution for that model, okay? It's a concrete solution. You could actually write down an algebraic solution or an arithmetic solution as well. Oops, it wasn't 19, it was 24. Okay? So the way that I solved it with the imagery is not the modeling, okay? The model is the actual language of the question. All right, here's the next one. This one's very different. It's called a missing add-ins model. Lelise needs to collect 10 leaves for a school project. She and Temeskin go out and find 8 leaves. How many more leaves does Lily say need? So on this one, she doesn't have 10 leaves and lose some, right? Nobody came in her bedroom and took them away. The dog did not eat her homework. None of that happened. She needs something that she does not have. Now, you might be thinking, but it's the same thing. And you're right, it is the same thing, but it's worded so very differently that can confuse kids. It doesn't sound the same. This doesn't sound like takeaway, right? It really doesn't. So when we're looking at writing this or drawing this out, I'm going to show you how you could draw this out in a way that makes sense. It says that she has 8 leaves, right? I've got 8 leaves right here. So I'm going to draw 8 leaves. All right, I've got 8 leaves, maybe you do too. But that's not how many we need. How many we need? We need 10. So I'm going to draw the next 2 leaves. I am going to draw them, but I'm going to draw them a little bit differently. That's a little bit better. All right. They're missing, right? They want to be there, right? There's dotted lines, there's dotted imagery. It's like I really need them to be there. And if I count them now, there's 10 represented in some fashion. And of course, the dotted ones are exactly what I need. So I need 2 more leaves. I don't start with something and take something away. I start with something and I need to add something else to it. Written out in words, or not words, but in an equation standpoint, it would look like this. I have 8. I need to add something to it, and it will equal 10 when I'm done. And the question, of course, what goes in this spot right here would be the number 2 as my answer. Okay, model 3. This is a comparison model. In this model, nobody's taking anything away and nobody's adding anything that's missing, okay? In this model, we have 2 people, in my description one, and they're playing a game, and we're simply trying to decide who has more points and by how many. So Madeline and Monique play basketball. Madeline scored 12 points. Monique scored 8 points. How many more points did Madeline score than Monique? This is not the same as either of the other 2 models. Still subtraction, but it's not the same. So what do we do? Well, again, I'll show you a concrete way of describing the solving of it. So this one says 12 points for Madeline. Madeline is first? Yes. So I'm going to actually just draw them in as hash marks, okay? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's Madeline. And then we have Monique. How many did she score? 8. There we go. I think that's 8. And the comparison then is when I sort of mark off what they have in common, the number that's here that I don't see present in Monique's line would be my solution. So it would be 4 points. You're comparing. Do I have to draw hash marks? No, I drew hash marks because, you know, points are not a physical object. Like I drew or attempted to draw leaves and rocks before because those are physical objects. So if there's a physical object that you're working with, you could certainly use a physical object as a drawing. This one just didn't really have that sort of picture to it. Last model. Our last model is the measurement model. And the measurement model It could take on any of the other three forms. So it could be a takeaway model, it could be a missing add-ins model, or it could be a comparison model, but it's always a measurement of objects. So it's like feet, or cups, or quarts, or degrees, okay, miles, those kinds of things that can be taken in measurement form. So here's Akeem. Akeem drives 15 miles to the mall, and he's on his way home, and his mom calls to ask him where he is. He states he's coming home, and he's driven 8 miles so far. How far is Akeem from home? So when we solve a measurement model, the idea is to solve it with a measurement number line, okay? So we're going to draw a number line. On one end of our number line is going to be Akeem's home, and on the other end is going to be the mall. So here's his home. That was a terrible home. And then we have the mall over here. I don't know. There's a whole bunch of going on in that mall. It's a big mall. And we know that the full distance between the two locations is supposed to be 15. So let's try and mark out about 15 between them. So here's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15. We'll call it good. You could label them all. You could label every other one. I'll do that. We'll call that. Okay. Akeem's mom called. He's gone all the way to the mall, so he's done this distance already once. And now he's going back towards home. And how far has he gone in his trek back towards home? 8. And as I go 8, I'm going to count them. Here's 1, 2, 3, 4, 5, 6, 7, 8. So this is where he is when mom calls. Where is he? What numerical location is he at? Yeah, he's at 7 right here. And that 7 is representing for us the distance he is from home. Right? 7 what? Miles. How else could we measure that kind of a distance? Anybody knows how things are measured besides miles? Kilometers. Yes, kilometers. I know we're in the United States, so we kind of think that, everybody else does what we do. It's not really true. Kilometers is another way to measure it. My point being, make sure that you are remembering to put the units, because that's not the only way to measure distances, okay? It's also measured in different distances besides just miles. Okay, so here's what you're going to do. I don't quite have everyone here today, but what we're about to do will work just as well. So let me see how many do I have. $17. That's a very prime number. Okay, 17. Let's see. Let's try to get into groups of 3. But that will mean that I have one group of 2 left over. Okay, so let's just do it kind of where you guys are sitting. So the 3 at the back, you guys group up. All right. The 3 here in the middle. So Emily, Julie, and Brittany, you guys are together. And then Ivana and Cameron and Kylie. Yes, Kylie. Okay, and then over here, I'm going to need, let's do you 3 in the group of 3, okay? So Rachel, Mackenzie, and Kira. All right, we'll do you guys, well, no, that's not going to work very well. Okay, so I'm going to let you be with the 2 of them, okay? So it's Hannah. Oh, I didn't even say I know your name. Your name is Hannah and Brooke and Kimberlyn. Okay, Hannah and Savannah and Samantha, you 3 are together. And then I've got Katie and Serena, and Katie and Serena. You guys are going to be my group of 2. Okay, so here's what you're going to do in your group. So turn your desk if you need to, and that's who you're going to be working with group work in a minute anyway. We've got just a tiny bit to do after this tiny group activity. We've got a tiny bit more, but here's what you're going to do. You're going to create a word problem for each of the 4 models of subtraction. You do not need to write out the solution. You don't need to draw the pictures, none of that. You're just creating the word problem, okay? So you're creating, the question that the child would be answering if they were working this problem out in your classroom. And I will ask for volunteers to give us what you've created. For you each get a volunteer at least once. So you're not really volunteering because I'm telling you you're going to volunteer. You're going to volunteer at least once to share with the class what you did on one of the examples, okay? So make sure that you are feeling comfortable with what you've chosen. All right, raise your hand, someone in your group, if your group's finished at this point. You're kind of finished. What is that supposed to mean?
We're on our last one.
Okay, you're writing the last one. Emily, where are you guys on?
We're on the second to last one.
Second to last one. Okay, Mackenzie, how's your group doing over there?
We're on the last
We're
one.
on the last one. Okay. Okay, take about 1 more minute to finish one up. All right, what do we have? I need a volunteer for group for takeaway. You want to do takeaway, Brooke? Brooke wants to do takeaway. Okay, what do you have?
I have 24 hours for the day. Civ takes 22 hours. How many hours do I have left?
Okay, cool. So we've got hours. You could actually group that into the measurement category too, if you wanted to, because hours could be divvied up. But it's definitely an example of taking away. Good. So I need one more example for takeaway. All right, Emily.
Okay. Dr. Whitlock has 6 Chick-fil-A fries, and B. Griffin takes away 2 Chick-fil-A fries. How many Chick-fil-A fries does Dr. Whitlock have left?
Fantastic. Somebody's stealing our fries. Okay, how about the missing add-ins model? An example of that. Somebody volunteer. Cameron.
Kylie was baking a pie, and she needed 6 apples. She already had 3 at home. How many does she need to buy at the store?
Yep, that would have been me right there. Notorious for forgetting things when I'm about to make baking. Awesome. All right, so we needed 6 apples. We only had 3, so we have to go find another missing add-ins one. I'm looking over here because y'all haven't shared yet. Somebody want to share your missing add-ins one? Mackenzie.
If Jack has 3 oranges and needs 6 oranges, how many more oranges does Jack?
All right, so he has, was it?
3.
He has 3 and he needs 6. That's funny. It's the same 3 and 6 that they used, isn't it? Yeah. Okay, very good. How about a comparison model? I need one comparison model and one number line model. 2 groups who are left. Katie, which one do you want to share?
Comparison.
Okay, what's your comparison
Joe
model?
has 5 pieces of pizza and Kira has 3. How many more pieces does Joe have than Kira?
All right, so comparison of our pizza. And up here in the front, ladies, Samantha and Hannah. What do you want to say for your number line model? What was yours?
The distance from Shawnee to Oklahoma City is 40 miles. Hannah started in Shawnee and is driven 23 miles. How much farther does Jim go?
All right, so distances to locations. Very good. All right, so turn around, if you would, kind of where you're sitting. We're not going to get to the group work that I thought we would, but it's totally fine. Let me finish up with you this lesson, though, because there's just a couple more slides on it. Whole number subtraction. We're checking to see which of these 4 properties we had for addition might work with subtraction. So closure. Remember, closure is the idea if I take 2, in this case, whole numbers, and I subtract them, do I get another whole number? Always. That's a good example. So yeah, this one is a no. It doesn't always work. And an example, which is what we would call a counterexample, right, to that would be something like 5 minus 7, which would be -2. And -2 is not an element of the whole numbers. Okay? So can we make it work on some numbers? Absolutely. But the question is, does it work for all? What do you think about commutative? Does commutative work with subtraction? Nope, it doesn't work either. Can somebody give me an example?
7 minus 5 equals 2. 5 minus 7 equals 2.
Right, so 7 minus 5 would have been fine, but 5 minus 7 was not so fine. And the gist on this one really has to do with the fact that these are not equal when I've done them at the end, right? Yeah. So commutative property doesn't work. I'm going to tell you, associative property doesn't work either. And let me give you an example for that one, just because I was a little bit strategic in how I wrote mine down. I'm going to do 3 minus 2 minus 1, and then I'm going to do 3 minus 2 minus 1. So if I do the first one, what is 3 minus 2? 1, and that 1 minus the other one would give me a 0. On the second one, what's 2 minus 1? 1, and then I have 3 minus that 1 to give me a 2. They're both whole numbers on this one example, right? But they're not equal. And that's what they would have to be in order for the associative property to have held. And the last one is the identity property. So we've got 3 strikes so far. Do you think this is strike 4? No? Yes? Do you think it works? It's tricky. So let's give an example. We'll use your same 7 from before. What's 7 minus 0? 7, and that's totally cool. But what happens when I do it the other direction? It doesn't work. So if there were such a thing as it, like halfway holding, kind of like commutative property, if it sort of halfway holds, not commutative, but the first one, what was it? Closure. It sort of halfway holds, but it doesn't hold in both directions. So this one does not work either. It's a no. We have none of those 4 properties that work for addition that will also work for subtraction. All right? Okay, so let me say this on here just in case somebody's listening outside and needs to know. So the homework group work is not going to be due on Wednesday. We'll do the group work in class, and then it'll be due on Friday. Okay? So probably it'll end up then that we will catch up over the weekend in terms of being back on track for our sections. But right now, this homework is not assigned. All right? So slip it away. So that means that if you're still working on test redos, that should be your priority, right? Absolutely.